So, let's talk about AI. It's everywhere these days. Chatbots, these crazy image generators, the whole deal. But what if I told you that underneath all that complex code, there's a deep, almost spooky connection to physics? Yeah, I know. It sounds weird, right? But stick with me because we're going to dive into this really strange and powerful relationship.
Okay, so to really get this, we need to rewind a bit. Picture this. It's October 8th, 2024. The whole scientific community is holding its breath, waiting for the big announcement from the Royal Swedish Academy of Sciences, for the Nobel Prize in Physics.
And who gets the prize? John Hopfield and Geoffrey Hinton. Okay, but for what? For their foundational discoveries in, wait for it, artificial intelligence.
So, hold on a second. The Nobel Prize in Physics for AI? That's the big question here, right? What on earth does machine learning have to do with the fundamental laws of the universe? Well, it turns out the answer is this incredible two-way street, and it's absolutely fascinating. All right, so let's start with part one, how physics basically gave AI its first big idea. And it all starts with something you probably have on your fridge right now, magnets.
So, way back in 1920, this student, Ernst Ising, gets a puzzle from his professor. The goal? Figure out how a regular chunk of iron becomes a permanent magnet. He came up with this really simple but brilliant model. Just imagine a grid of atoms, right? And each atom has a tiny little magnet inside, its spin, that can either point up or down. The real magic, though, wasn't just the spins themselves, but how they all talk to their neighbors.
And this is where we get this crucial idea called an energy landscape. Think about it like this. Picture a marble rolling over a bunch of hills and valleys. Where is it going to end up? Well, it's always going to try to settle in the deepest valley it can find, right? That's its lowest energy state. It's the exact same idea for the atoms in a magnet. They naturally want to relax into their most stable configuration, which means lining up with their neighbors. Okay, now fast forward decades later to 1982. A guy named John Hopfield has this total light bulb moment. He looks at this physics model for magnets and thinks, wait a minute, I can use this for computation. So he takes the model and just swaps out the parts. Instead of atoms, you have artificial neurons. Instead of spins being up or down, you have neurons being active or inactive. And he kept that same core idea of an energy landscape.
And this, right here, is how a Hopfield network actually remembers things. It's amazing. You can literally sculpt the energy landscape of the network. By tweaking the strength of the connections between all the neurons, you're basically digging these deep valleys that correspond to a specific memory, like a picture. So then, if you give the network a blurry or incomplete version of that picture, the system just naturally rolls downhill and settles into the bottom of the nearest valley, recalling the perfect, complete memory. It's wild. Physics literally handed us the blueprint for machine memory.
But wait, that's only half the story. That's how physics inspired AI. Now things get really weird, because that two-way street I mentioned, it's coming back the other way. AI is now starting to inspire and even solve some of the biggest problems in fundamental physics. Okay, to get this next part, we just need one quick concept from physics, the idea of a field. And don't worry, it's simpler than it sounds. A field is just something that assigns a value to every point in space. Think of a weather map showing the temperature across the country. That's a field. And believe it or not, a neural network, which takes in some numbers and spits out other numbers, can be thought of in the exact same way, as a kind of mathematical field. All right, now this is where things go off the rails, in the best way possible. Back in 1995, a researcher named Radford Neal asked a pretty crazy question. He said, okay, what happens if we take a neural network and just make it infinitely wide? Like, what happens when you just keep adding more and more and more neurons? Now, you'd think the answer would just be chaos, right? A total mess. But no, something absolutely incredible happens. As the network gets wider and wider, the pattern of its outputs, if you just randomly tweak its settings, it doesn't get messier. It actually gets smoother and way more predictable. In fact, it settles into a perfect bell curve. You've probably seen it before. Mathematicians call it a Gaussian distribution. It's this beautiful, predictable shape. And this was a mind-blowing discovery, right? This deep, perfect statistical order was just emerging out of this insanely complex system. Nobody expected that. And here's the kicker. Physicists saw this result and their jaws just dropped because they had seen that exact same pattern before. Where? In the simplest possible model of a quantum field. You know, the stuff that describes the fundamental particles of the universe. When you look at its random fluctuations, guess what shape you get? A perfect Gaussian distribution. So get this, an infinitely wide neural network behaves statistically in the exact same way as a basic quantum field.
It's not just kind of similar, it is the exact same mathematical fingerprint. One for a computer program we built, and one for the very fabric of reality.
So, is this just some weird, quirky coincidence? Absolutely not. This deep connection is actually giving scientists in both fields a brand new and super powerful set of tools to play with.
For physicists, this is a total game changer. I mean, trying to calculate the behavior of quantum fields is ridiculously hard. But now they can use these neural networks almost like a simulator. They're using them to tackle just massive challenges. Things like figuring out how quarks behave inside an atom, cleaning up the signals from colliding black holes, or even mapping out the invisible dark matter that holds galaxies together.
And remember, it's a two-way street. We're always hearing about how AI is a black box, right? We know it works, but we don't really know how it's thinking. Well, now we can use the trusted language and tools of physics, things like those energy landscapes we talked about, or even famous tools like Feynman diagrams, to peer inside that black box. It helps us translate what the AI is doing into a language we already understand, making the whole thing a lot less mysterious.
So what we're really seeing here is the beginning of this incredible fusion. The study of intelligence and the study of the universe. They're starting to become the same thing.
I love how one group of researchers put it. They said that these ideas from physics are building a bridge, a way for us to finally translate the weird new world of AI into the language we've used to describe the universe for centuries.
So if there's one thing to take away from all this, it's this. What's happening inside these AI models isn't just a bunch of random math. It's actually echoing the very same statistical laws that govern the particles and fields that make up everything at the most fundamental level of reality. And that leaves us with a really deep, kind of mind-bending question. I mean, nobody saw this connection coming. And it really makes you wonder, is intelligence just a clever computational trick we figured out? Or is it something way more fundamental? Is it an emergent property of the universe itself, just like gravity or the flow of time? We don't know yet. But as these two giant fields continue to merge, that might just be the next great secret they unlock together.